So now we are going to make the Clapeyron diagram. So it's PV. So first of all, before doing the diagram, it's important to know that every single transformation has its own shape for the curve as an identity. So you just have to learn these curves, and every time you have to make the diagram, you need to make the real shape that is corresponding to the transformation that you are considering here. So it's going to be here, the first one is adiabatic, so we have this shape for the adiabatic curve. Now the question is, where is the initial state and where is the final state? That is a very important question because it's going to allow us to know where to start the next step. Is it here or is it here? So in order to answer that, we are going to go check out the nature of the transformation, except the fact that it's adiabatic, it's a compression. Compression means that the volume is decreasing. So necessarily you have the initial volume that is bigger than the final volume. So we'll have this. Have V0 and V1 like this. So if this is V0 and this is V1, then your arrow is always in the sense of the time evolution. So necessarily here we start at the state 0 and we go to the state 1. So it's going to be like this. So this is the state 0, this is the state 1. So now that we know that the final state of the first step is here, then we are able to start the drawing of the second step. That's why the sense is important, because otherwise if it was in the other sense, this will be the ending of the transformation. But now, as we are actually in that sense, that is where we are going to start the next step. The next transformation is isochoric. Isochoric means that the curve is a straight line, which makes sense actually because as you know, the abscissa is the volume and isochoric means volume constants. So the arrow is like this as the pressure is decreasing, as we said in the previous page. And then for the last transformation, it's an isothermal. The isothermal transformation is going to bring us to the initial state 0. And that is the shape of it. So as you can see, the adiabatic shape and the isothermal shape are very similar, but there is a difference. The isothermal is actually, the curvature is more pronunciated for the isothermal case. So I'm just going to specify everyone. So this was the adiabatic. This is the isochoric. And this is the isothermal. So this is the Clapeyron diagram for this question. Obviously, this is P1 and that is P2. And this is P0. So now we are going to make the next question, but before jumping to the next question, there is a remark that we can do. When you look at the sense of the arrow, actually you can know from the beginning if your cycle is a motor cycle or a receptor cycle. Remember, a motor cycle means that your system is giving away the mechanical energy to the outside, and receptor cycle means that your system is taking the mechanical energy from the outside, so it's receiving it. But so in our case here, the sense of the arrows is a counterclockwise sense. If it was a clockwise sense, it means that it's a motor cycle. But if it's a counterclockwise sense, it means that it's a receptor cycle, which is our case here. So we're just going to write that. Something that we can deduce from the beginning is the fact that if it's a receptor cycle, it means that the work of the total cycle, when I'm saying total cycle, I mean that it's the resultant work, the summation of the work between 0 and 1 plus work between 1 and 2 plus work between 2 and 0. So this resultant work then is going to be positive because it's a receptor cycle. So I'm just going to add a sentence about the fact that the mechanical energy is here received. Okay, so now I'm just going to change the page and to the next question. For the next question, we want to calculate T1 and P2. Actually, P2, we did the answer already. When we were doing the notes in the beginning, I told you that we can deduce P2, remember? So we did actually this part of the question. And for T1, we are going to make it. So how to deduce T1? Remember, the transformation between 0 and 1 is an adiabatic transformation. So that being said, we can directly go apply the Laplace Law. That is just for adiabatic transformations. PV power gamma equal to constant. That's the law. So what we are going to do now is to apply this law for the state 0 and then for the state 1 and see what happens. So we have P0 V0 power gamma equal to constant, P1 V1 power gamma equal to constant, and it's actually the same constant as it's the same transformation between 0 and 1, that is adiabatic. So that is equal to this. And if we have this equality, then we can write P0 V0 power gamma equal to P1 V1 power gamma. So this is actually correct. And once we do this, then we can continue the process. We are going to replace V1 but by what we wrote in the beginning, if you remember. We said that V1 is V0 over 3. Also, something else that we will replace is the P1. So how are we going to replace P1? We are going to use the perfect case law. So I just apply that. I express the P1, and then I replace that expression inside of my equation. So once I'm doing all the replacements that I will have, so now it's the turn of V1 that I'm going to replace by V0 over 3. But before doing this replacement, I'm just going to specify something, mathematical thing that is useful. I'm going to have nRT1, V1 power gamma minus 1. Why do I have this power? Because actually in mathematics, when you have 1 over a, that is equal to a power minus 1. And this is exactly what we have here for V1. We have 1 over V1, which means that it's V1 power minus 1. And we had already this one, so we just add to gather the powers together, and this is what we obtain at the end. So let's come back to the process. So now I'm going to replace V1 by V0 over 3. And once I have that equation, now I'm actually able to express T1, because remember, the purpose of this question is to express T1, right? So this is why I went replacing P1 by something that is depending on T1, so that I can have it and extract it from the rest. And this is what we're going to do now. So I'm going to write the expression that we had. Okay, so now I want to express T1 as I said, so it's going to be this. So why do I have that? It's because actually, as you can see, I have V0 power gamma here and the V0 power gamma minus 1 in the other side. So if I bring this one in the other side, then I just need to gather the powers again, and that is what I have at the end. So I'm just going to continue to simplify this. Actually, if you want, you can stop here. But if you want to express T1 in terms of T0, which is what we want to do, you need to go further again in the steps. So T1 in terms of T0. So in order to do that, we are going to continue the replacements this way. So the P0 V0 is going to be replaced. According again to the perfect case law, I'm going to replace this here. And I will have T1 that is and now I need to simplify the NR, and the final result is this one. So that is the answer to the question. We cannot simplify more than this for the T1 expression. And then for the second part of the question, we want to have P2. But as you remember in the beginning of this exercise, we expressed already P2 in the notes, if you remember. So this is the result that we had. Now we are going to go to the next question. So for the next question, we want to make something very classic. It's the calculation of the work, the variation of internal energy, and the calculation of the heat for every single step. So let's start with the first one. First was an adiabatic. For an adiabatic transformation, the heat is equal to 0, as you know, always. So if I apply the first law of thermodynamics, delta U equal to work plus heat, then I can tell that as the heat is 0, I have finally just delta U that is equal to the work. So I just need to express the work, and then that's it. the work for an adiabatic transformation is CV delta T, okay, by definition. So as you remember, we just need to make the replacements. So CV T1 minus T0, as T1 is the final state here. And I'm going to replace T1 by the expression that I just had a few minutes ago now in the previous question. So if I do this, that's what I have. Finally, I'm going to factorize by T0. And this is the final result that I have here, which is positive. So if my work is positive during this specific transformation, it means that during this specific transformation, again, I insist on that because I'm not talking now about the whole cycle, just about this time. Then the work, the system is receiving mechanical energy from the outside. So now we are going to make the next step. From 1 to 2. That was isochoric. For an isochoric transformation, always the work is equal to 0. So go check out the video about isochoric if you want more details about that. So that being said, again, we're going to use the first law of thermodynamics. So if we use that, it means that delta U in this case is equal to the heat. So let's calculate the heat. So again, the heat for isochoric transformation, we use again the formulas of the memo. So it's going to be equal to CV delta T. So it means that it's CV times the final temperature T2 minus initial temperature T1. I'm going to make the replacements. As you remember, in the notes of the beginning, we said that T2 is T0, and T1, according to the previous question, it was this expression. So I'm just going to replace for both. And this is what I will have. So actually, when you compare these two expressions, you can remark that they are just almost the same, but inside of the bracket, it's reversed. The sign is reversed, okay? So this is actually negative this time, which means that for this transformation, the system is giving away the thermal energy to the environment, the external environment. So now we are going to make the last step, which is the isobaric, no, the isochoric, if I will remember. Well, the isochoric was the second one, is actually the isothermal, the last step. Okay, so I'm just going to change the page. From state 2 to state 0, and we said that it is the isothermal transformation here. So if it's the isothermal transformation, then we are going to say that delta U is equal to 0. Again, you can go check out the isothermal case to know more details about this again. So for the first law of thermodynamics, if delta U is 0, then the work is equal to minus the heat. So now I'm going to calculate the work. So integration of minus p dv between the state 2 until the state 0. Okay, so be careful about the boundaries. Don't forget that the state 2 is the initial state. Even if 2 sounds bigger than 0, don't get confused. 2 is actually here the initial state, and then we go to the state 0 as it's a cycle. And here I recommend you to identify the variable that you have for the integration and directly to replace your boundaries by the variable that we consider. In our case, it's the volume because we have dV, so it's going to be V2 and V0, and we have minus P dV. So once we do that, then there is something that we need to do again because the pressure is not a constant here. We are not in isobaric case, we are in isothermal. So if the pressure isn't constant, we need to express it in terms of the volume, as the volume is our variable of integration. And how we are going to do that, we are going to use again the perfect gas law, PV equals to nRT, which means that P is equal to nRT over V. And now I'm able to take this and replace directly inside because actually the temperature is constant, so I'm able I'm allowed to take it and just consider it as a constant. So let's continue. We'll have minus nRT 1 over V dV. So all the constants are outside of the integration now, including the temperature. And now we just have to integrate 1 over V. So as you remember, the primitive of 1 over x is ln of x. So it's going to be ln of V here. Between V2 and V0. And as you remember, V2 is actually V0 over 3, but we will make this replacement later. For now, just let's do the difference. Ln of V2 minus of V0, okay, minus ln of V2. So let's do that. We are going to have here minus nRT ln of V0 over V2. So in order to do that, I just choose the mathematical law that says when you have ln A minus ln B, it's actually ln A over B. So this is what I used here. And then once I have this, I'm going to replace V2 by V0 over 3 that we specified in the beginning of the exercise. So it's going to be minus nRT ln of V0 over V0, and the 3 is going to be in the top as we reverse the ratio, which means that at the end of the process, we just have nRT ln of 3. And that is what we have for the result of the work for the last transformation. So this is going to be negative, obviously. So the work is negative, which means that during this step, the system is giving the mechanical energy to the environment. So remember that the heat is minus the work here. So it's minus the result that we had. And it's actually positive, as the other one was negative. So now we are going to make the last question. So for the last question, it's going to be actually the calculation of the resultant work and the resultant heat. So the resultant heat, W cycle, is the summation of all the heats that we have, of all the works that we had. So it was W01 plus W12 plus W23. So as you remember, 1,2 transformation is isochoric, so this is 0. And then we just have the two others that we will just replace. So why did I write P0, V0? I'm going to explain you this right now. Remember, for the work that was W20, the result that we had, remember, so it was minus nRT ln of 3, remember? But according to the first law of thermodynamics, PV, so let's apply this to the 0 situation, okay? nRT0. Yeah, I didn't specify, but it was T0 as it was isothermal. It makes sense, obviously. So if I replace this here by this, it works. It's exactly the same expression. So that's why I kept this expression here. It's the same thing. So now we are going to continue the process. I'm going to replace this by the result that we had, if you remember. I'm also, in the other hand, going to replace CV by this formula. So just to remark here, CV has a lot of expressions that you have to know for sure because we are replacing them all the time. This is one of them. By definition, we have CV like that. And then we are going to make the replacements. So it's going to be equal NR over gamma minus 1, 3 gamma minus 1 T0 minus NR T0 to ln 3. And if I simplify that again, that's what I have. And this is a positive equation. So finally, the work of the system, the resultant work, W cycle, is positive. And this is exactly what we were expecting in the first question of the exercise. If you remember, when we were making the analysis of the graph, because of the sense that was counterclockwise, we deduced the fact that the work has to be positive because it's a receiver cycle. And this is verified here. So now let's do to the next page to make the calculation of the work, of the heats. So the resultant heat is the summation of all the heats that we have. So as you remember, the 0,1 was 0 as it was adiabatic. And then we just need to make the summation of the two others. So it's going to be this result that we have here, and it's going to be P0, V0, ln 3. And actually, if you have, if you notice the expression here, if you compare it to the previous one, I mean, you will notice the fact that this is the opposite of what we had for the heat, for the work, sorry. So it's minus W cycle. So that being said, it means necessarily that the Q, the heat of the cycle, is actually negative as the work was positive. So we can tell that as a conclusion for this cycle, which is a receptor cycle, it's going to receive the mechanical energy from the environment and it's going to give thermal energy to the environment. make is the summation of the internal energy, and you will find that it's 0. And this is exactly what we were expecting, because by definition for a cycle, delta U is always equal to 0. That's a definition. So this is verified here. If we try to make the calculation, it works also in this case. So this exercise was very general because we saw 3 kind of transformations in here. So the isothermal, the adiabatic, and the isochoric. Obviously, if you have any question, you can ask.